Okay, recording started.
Okay, we'll wait another minute, Sarel, so feel free to take another sip from that coffee.
First sip.
Okay, I think so. We're live and we're recording.
Okay, great. Wait a few more seconds. Hey, hi everyone. Welcome to session 10C on data structures. We have an exciting program here with several breakthrough results, so looking forward to it. We have an additional, we actually have 5 talks in this session, not 4 as scheduled. So Erica Bolkonski is going to talk about submodular minimization in the end of this session. And you probably know the drill by now. So it's a 5-minute presentation followed by a 5-minute Q&A. And you should feel free to raise your hands or post Q&A questions. We're going to defer them to the end of the presentation. And if we have kind of spillover Q&As, we're gonna defer them to the end of the session, and we might actually hang out for another 10-15 minute as this is the last session. So I believe depending on the interest of the crowd. So without further ado, I'm happy to introduce Sarel Cohen from Tel Aviv University, who's going to talk about distance sensitivity oracles, faster distance sensitivity oracles. So Sarel, the stage is yours.
Hey, hi everyone. I'm Sarel. Thanks, Omri, for the introduction. So in this talk, I will present distance sensitivity oracles with subcubic preprocessing time and fast query time. This is joint work with Shiri Chechik. So what are distance sensitivity oracles? Given a graph G, and in this work, we assume that G is a directed graph with integer edge weights in the range -m to m. We want to preprocess it into a data structure such that given queries of the form a vertex S, a vertex T, and either an edge E or a vertex V, we want to compute the distance from S to T in the graph G minus E or G minus V. We describe previous results of distance sensitivity oracles for the case of a single edge or vertex failure. The Pătraşcu et al. Presented a distance sensitivity oracle with O of n square log n space, constant query time, and O of m n square preprocessing time. Bernstein and Karger in SODA 2008 and then in STOC 2009 improved the preprocessing time to O tilde of mn, keeping the same asymptotic space and query time. This is near optimal due to the conditional lower bound for combinatorial all pairs shortest paths. An interesting question is whether one can improve the preprocessing time to be subcubic using fast matrix multiplication. In Fox 2010, Wayman and Houston presented the subcubic distance sensitivity oracle for directed graphs with integer edge weights in the range -m to m. Its preprocessing time is subcubic, O tilde of m n to the power of omega plus 1 minus alpha. Here alpha is a parameter between 0 to 1, which presents a trade-off between the preprocessing time and the query time. And omega is the matrix multiplication exponent. And the query time is subquadratic. It is O tilde of n to the power of 1 plus alpha. So just a remark, the result is for multiple failures, and here we present it for the case of a single failure. Later, Grandoni and Vasilevska-Williams presented in Fox 2012 a distance sensitivity oracle with subcubic preprocessing time and sublinear query time for a good choice of their parameter with this value of alpha and with omega that equals to 2.373. Then their preprocessing time is O tilde of mn to the power of 2.873 subcubic, and their query time is sublinear O tilde of n to the power of 0.7. And an interesting following question would be whether one can develop a distance sensitivity oracle with subcubic preprocessing time and polylogarithmic query time. In this paper, we answer this question affirmatively by presenting a distance sensitivity oracle with the same O tilde of mn to the power of 2.873 preprocessing time and polylogarithmic query time. And I will try very shortly to somehow give intuition into the techniques we use. We will assume for simplicity of presentation that all shortest paths are unique and that edge weights are positive integers in the range 1 to m. In the paper, we remove these assumptions. So let us use the following definition. The shortest path from S to T is denoted by PST, and the replacement path PSTE is the shortest S to T path that avoids the edge E, and without loss of generality, we may assume that the replacement path is composed of a common prefix with the shortest path, a disjoint detour, and a common suffix with the shortest path. We consider 4 cases for a query STE. Case 1 is when there exists a short replacement path containing at most 3 R edges. Here, R is a parameter that we set later on in order to minimize the preprocessing time. Case 2 is when there exists a replacement path with either a long prefix or a long suffix containing at least R edges. Case 3 is when the edge E is among the first or last R edges of the shortest path. And case 4, which we refer to as the R critical case, contains all the queries that do not belong to either case 1, case 2, or case 3. So cases 1 to 3 are easy to handle using prior work. And case 4 is the most technically difficult part of our paper. So in very high level, to handle case 4, let's assume that we have a vertex S, a vertex T, and a vertex V that is on the detour of the replacement path. We use the first binary search to find the first common edge of the shortest path from S to T, the shortest path from V to T. We denote it by EI. And then if we enumerate the vertices along the shortest path from V to T, then we basically search in a table that we use a table that stores a subset of replacement paths for the edges on the shortest path PVT. And then we use a binary search to find the last replacement path that departs before the first common edge and re-enters in the last R edges. And this is the subpath of the replacement path from V to T that avoids the middle part. And then we stitch it with a similar one from S to V. And this is a very high level in the time that we have. So thank you if you have any questions.
Okay, thanks, Sarel. Any questions from the crowd? All right, Actually, I have a question. So the space of your data structure is also n squared?
Okay, good question. So the space is n to the power of 2.5. And it's basically, we take we do another step to improve it. I mean, if you take the space as is, then it's a bit higher. But then we have a last section that we improve it, where instead of computing a set of distances, we compute a set of on several graphs. For example, graphs that obtain in Weyman-induced results, and the randomized graphs, we only store we only take distances over there, and instead of computing explicitly a set of distances, we simply use this distance, use these distances to compute in polylog n time the distance. So instead of explicitly storing many distances, we use these graphs and only compute distances in them instead, and use them to deduce the distance, which also reduces the space. So.
Thanks. Another question. So can you give intuition for why? So you said the pre-processing time is not n to the omega, it's n to the omega plus half, right?
Mm-hmm.
Can you, and this seems to appear in prior works as well, this plus half, right?
Yes. So why is it plus half? So first of all, we use prior work. So we sample a subset of vertices, B, which every vertex is sampled with probability C log n over R for large enough constant C. So the size of B is O tilde of n over R. And so in the first version with higher preprocessing time, we compute a single source replacement paths, which takes mn omega time for every such vertex. This is too much. I mean, we compute other things, but this becomes the bottleneck. And then in the second step that we do to improve the preprocessing time, we basically compute this single source replacement path of Grandoni and Vasilevska-Williams only for a subset of square n vertices. So this is omega plus half, right? So mn omega times square n, it's mn to the power of omega plus half. And for the rest of the vertices, we do something else using the random graphs of Weyman and Euster, as we described in the paper. But here's, for example, one way that we get to this bottleneck of mn to the power of omega plus half.
Okay, and it's clear that n to the omega is a lower bound, right? Because just for computing APSP or something like that, or is that not clear?
Yes, so mn omega plus half is a lower bound. So the mn omega plus half is for omega that is it's not for all omega. It is for omega that is bigger than something. We state the number in the paper. For omega that is between 2 to this number, it's a bit more than mn omega plus half. For if it was mn omega plus half for omega that equals 2, then indeed it was matching the APSP time in this case. But it's so for it's mn omega plus half for omega that is above some constant but below the best known constant.
All right, thanks a lot, Sarel. I guess any more questions? All right, thanks, Sarel. I think you can stop sharing your screen.
Okay, thanks everyone, goodbye.
Thanks. Okay, great. Our next speaker is Pătraşcu Yu from Princeton. He's going to talk about another breakthrough result on nearly optimal static Las Vegas dictionaries. So, Pătraşcu, the stage is yours.
Thanks for the introduction. So I'll give a brief introduction to my results about dictionary data structures. Okay. So what is dictionary and what does it do? The one problem it solves is this membership testing. And in membership testing, we're giving a set of n keys from a universe of size u. So we think each key is a number between 1 and u. And I think u is bounded by poly n. And then we would like to preprocess this set into a data structure supporting membership queries. In each membership query, we're giving another element from this universe x. And we just want to know whether this x appears in the input or not. So this is a very basic data structure problem. And I guess the most common well-known solution to it is by random hashing, right? So we just randomly hash the input keys into n buckets, and then say use a linked list to store all the keys that are mapped to the same bucket. And then if the hash function is good, then it has constant expected query time. And what is the space of this data structure? we have n keys to store in different buckets, and each key takes log u bits to encode. So roughly the total space of this random hashing is just n log u bits. And it turns out that you can improve this query time to constant worst case by applying techniques like perfect hashing, which basically hashes all n keys into distinct buckets. So one key per bucket. So these random hashing-based techniques solve this problem with optimal or best possible query time. So does it also use best space? It turns out that the answer is no. So suppose we don't care about query time and just want to store the input set. So there are n keys from universe of size u. So in total, there will be u choose n different inputs. So if we don't care about the query time, then the optimal space to store the set is just log of u choose n bits, which is roughly n log u over n plus O of n bits. So in this case, when u and n are very close, this is actually asymptotically smaller than n log u. But even in general, when u is just bounded by poly n, there is still a constant factor gap between these two. And it turns out that for this problem, for dictionary, we can get very, very close to optimal space, but also get optimal query time. So the previous best known data structure for this problem is due to Pătraşcu. And this data structure only uses log of n choose u plus n over polylog n bits. So it's only like 1 bit per polylog n input keys, extra bits. And then it also has a constant worst case query time. And for such data structures that only use a little of one extra fraction of extra space, or in other words, the extra space is a low order, those data structures are called succinct data structures. And this is also the focus of this paper. And in general, in succinct data structures, we would like to know how large this extra term has to be when the query time is very low or even constant. So does it have to be close to linear, like in this case, or maybe it can be n to the epsilon, or maybe polylog n, or even constant. So in this paper, we show that if we allow randomization, then for this problem, this extra space can be reduced significantly to polylog n. The main result of this paper is a new data structure for dictionary that uses space log of u choose n plus only polylog n bits. And it also has a constant query time, but in expectation. And also this is assuming that the query algorithm has access to a data-independent lookup table of size n to the epsilon. So what is this lookup table? It actually depends on the model of computation and the query algorithm. So to be more specific, given two integers bounded by poly n, what do we assume that can be computed from them in constant time? So I guess the basic assumption is that we can do arithmetic operations like add these two numbers, and we treat them as bit strings and do bitwise operations to them. So on these basic assumptions, we will need this extra lookup table. This is because in the query algorithm, we actually need to do compute more complicated functions on them, and it's not clear whether they can be computed in constant time based using these basic operations. And this lookup table just stores the truth table of those functions. And the point here is that this table is independent of the input keys, the n keys, and it only depends on the model of computation and the query time. So on the other hand, if we just store this table as a part of the data structure, so we don't need anything else, the space bound becomes log of u choose n plus n to the epsilon, and this is still an improvement over the previous best known. Also, I just would like to mention that this extra polylog n bits are just random bits. So the preprocessing algorithm will just generate these random bits independent of the input. Then it looks at these random bits and the input itself and design a data structure that only takes log of u choose n plus 1 bit. And then the final data structure will be the concatenation of the two. So the true size of the data structure uses only 1 extra bit. But I guess due to time constraints, I want to be able to talk about the construction of the data structure even at a high level. But there's a longer version of this talk on YouTube with more details, which contains a link to an even longer version of this talk with even more details. But in this talk, let me just stop here with my slides on the open questions. So any questions?
Questions to Huacheng? So watching in the bit probe model, there is actually a logarithmic lower bound, a redundancy lower bound, right?
Yeah, I think so.
Right. So yeah.
Yeah, so I guess in this data structure, we heavily use the fact that we can look at like log n bits of the data structure at once. So this assumption is also used in like hashing-based techniques. You need to check whether your key matches the key that is stored in the bucket that takes log n bits.
So what do you think is the answer? Is there a constant redundancy, or log n is the best possible?
You mean bit probe, or sorry, you mean
cell probe?
cell probe, deterministic, or
Las Vegas is fine.
Las Vegas, yeah. I think we need a few extra bits because if the algorithm is randomized, then we at least need to store the extra random bits in the data structure if the query is randomized. And these random bits will take some space. Like here, we're using polylog_n random bits, and that's the most of the redundancy.
I see. So can you kind of demystify this? It sounds counterintuitive that with one bit you can, you can have constant query time. Can you say?
Yeah. Okay. I guess maybe all I can say now is somehow in this data structure there are many queries, and then we can ensure that most of the queries can be answered with probably they can be answered in constant time, and this most of queries is like 1 minus 1 over polylog_n fraction, and then the other 1 over polylog_n fraction of the answers are the hard queries are the hard queries, and they are in fact solved by the previous solution, some other data structure that is similar to the previous solution that uses 1 bit and log_n query time. So I guess the one I mentioned here, this one with n over polylog_n bits and constant query time, there's a trade-off that allows you to do 1 extra bit but log_n query time. So I guess here we still have this worst case time, but it only applies to a very small fraction of the queries. And the random bits are used to ensure that this random set is a random set. So for each query, in expectation, the time is constant.
I see. Yes, and I also think it answers Sefer's question. So Sefer is asking about worst case query time. Sefer, does that answer your question? I'm not sure.
So I guess maybe let me just answer this again. So the worst case time is still log_n. Even if we don't care about mode of computation, just in the cell probe model, and then we have free randomness, the worst case is still log_n.
Okay, maybe great. A last question. So all those perfect hashing techniques, they're inherently static, right? You cannot achieve all those things dynamically, right?
Yeah, so yeah, that's one open question that I don't know. So at least for this data structure, in order to handle updates, you would need probably nearly linear update time. Unless you use more space, maybe you can reduce the update time.
Okay, great. Thanks a lot for watching. I think you can stop sharing the screen. Great. Our next speaker, also on succinct data structures, is Mingmo Liu from Princeton. From Nanjing University. This is another joint work with Watching. So Mingmo, stage is yours.
Okay, thanks for introduction. I am Liu Mingmo. In this talk, we study the lower bound for succinct range minimum query. This is a joint work with Yuhua Chen. Okay. Range minimum query, aka RMQ, is a classical data structure problem. In this work, we study a variant of RMQ, which asks for the index of the minimum. The RMQ is a fundamental problem which has numerous applications in computer science. RMQ is equivalent with the lowest common ancestor problem for binary trees. The equivalence is established via a structure named the Cartesian tree. Therefore, one may conclude that the input is in fact a binary tree. RMQ has a classical textbook solution, which uses ON space and constant time. But the input is in fact a binary tree, so the size of input universe is a Catalan number. The logarithm of nth Catalan number is 2n minus O log n. Therefore, the truly linear space should be ON bits and using ON over log n words if the word size is log n. Consequently, we choose the uniform distribution over all n-node binary trees as a hard distribution to prove the lower bound. To the best of our knowledge, the best data structure for RMQ uses 2n plus n over polylog n bits and constant query time. Naturally, two questions come to our mind. Is there a lower bound for RMQ? Is the state-of-the-art data structure optimal? In this work, we presented the first lower bound for RMQ. Our lower bound shows that the state-of-the-art data structure is optimal in the regime of constant time. We prove the lower bound in the CLPRO model. It is very similar to the famous RAM model. In the CLPRO model, operations are free except memory access. So the time complexity is the number of memory accesses. In fact, we prove a lower bound for a spatial potential search named PREDZ. We believe PREDZ characterizes the hardness of RMQ. At first, we reduced PREDZ to RMQ. Then, we show lower bound for PREDZ. In order to do this, our strategy is a new round elimination on carefully choosing hard queries. The classical round elimination is developed by Pătraşcu and Viola in 2010. Their proof uses a variant of round elimination in a tweaked CLPRO model. In this model, a data structure may use 2n bits of space and extra p published bits. So the space complexity is 2n plus p bits. The published bits may arbitrarily depend on the database. It also can be accessed by CPU for free. Pătraşcu and Viola argue that for data structure in this model, we can publish some cells to save one time of memory access for many queries. By recursively applying this argument, we obtain a data structure that uses some published bits, but doesn't access any memory cell. So the number of published bits in the final data structure can't be less than the information theoretical lower bound. The proof of the round elimination lemma is an encoding argument. We show that if the set of the cells probed by some queries is disjoint with some chosen cells, we can compress the whole database, achieving a too good to be true representation. It is feasible since the answers of queries are correlated. So we can publish some cells probed by some queries to save memory access. Unfortunately, the argument of Pătraşcu and Viola doesn't work for RMQ. Because their argument works for the average case lower bound, but we believe that RMQ has efficient average case solution. We move our concern to a set of hard queries, which are precisely the data points, and we apply round elimination on the hard queries only. At first, we spend some bits to specify some queries to pub. such that the answers of these queries reveal lots of information. If many hard queries do not prove the sales proved by QPAP, we can recover many data points with the sales which are not proved by QPAP. So we show that with the data points we can recover and a short auxiliary bit string, we can fully recover the database. In other words, we can compress the sales proved by QPAP. But how can we know which sales are not proved by QPAP? To solve this problem, we choose a good L. We write down the first L-1 sales proved by QPAP, so we know the addresses of the L cells automatically. Then we compress the L cells proved by QPAP. By putting everything together, we obtain the round-elimination lemma. By recursively applying the lemma, we have the lower bound for pretty Z. Finally, we have the lower bound for RMQ due to our reduction. In conclusion, we prove the first lower bound for RMQ. Our lower bound shows that the state-of-the-art algorithm is optimal in the regime of constant time. The lower bound is proven by reducing from pretty Z. We find the new ways of proving worst-case lower bound and attacking fully adaptivity to prove lower bound for pretty Z. There are some interesting open problems. Can we close the gap between the lower bound and upper bound for RMQ in general case? Is there a more powerful tool to deal with the adaptivity? That's all. Thanks for your attention.
Thanks a lot, Mingmo. Questions? Anybody? So Mingmo, actually, what did you, maybe I missed this, but did you actually define what is the pred-Z problem exactly? Is it a predicate?
Okay. The pred-Z. Okay.
Sorry.
The pred-Z, the pred-Z has these sub-problems. Each of them is a potential search, and it has a large integer Z.
Sorry.
So it was required to support two kinds of queries. First is to answer potential search on some sub-problem or return the Z.
I see. And so you mentioned adaptivity. So can you get a stronger lower bound for non-adaptive queries?
Yes, yes. If we assume non-adaptivity, we can prove a lower bound matches with the upper bound. Yes.
I see. Okay. Great. Any more questions? All right. Thanks a lot, Mingmo. I think we can stop sharing the screen. Thank you. We're moving on to the fourth talk of the session by Lingxiao Huang on core sets for clustering in Euclidean spaces. Lingxiao, ready when you are. Lingxiao, you might be muted, maybe. Oh, we need to unmute you. Sorry.
Okay. Okay, it's okay now?
Yep. Go ahead.
Okay. Okay, thank you. Thank you for coming to my talk. This is John Work with MINIMIZATION. We consider the core-set construction for the clustering problem in Euclidean space RD. And the goal of the K-set clustering problem is to compute K-centers such that the sum of base-power distances from each point to the center point is minimized. And an epsilon core set is a weighted point set as such that for any K centers, we can compute a weighted clustering objective over the core set, which is always a good approximation for the clustering objective over the original data set. And note that this weight function is necessary. So an important tool, a widely used tool for core set construction is called importance sampling. We first compute sensitivities for all points, and then take samples from a distribution proportional to these sensitivities. I will not discuss what sensitivities exactly, but roughly sensitivity measures the importance of each point, and we can compute sensitivities very fast. So just need all MDK time. And by this approach, Feldman and Lemberg show that an epsilon core set can be constructed in polynomial time with size only O tilde dk over epsilon to the 2z. So the problem is that the dimension d can be large up to n. So could we remove this size dependence of d? The idea is to apply dimension reduction. So we take a k-median z equal to 1 as an example. This gamma, this line gamma is a subspace, and we define pi x to be the projection of a point x to this subspace gamma. And consider an arbitrary k center set C, and this plane is the span subspace of gamma and C. And we define pi cx to be the projection point of x to this subspace. And Solar and Wuzhov show that, in fact, there exists a subspace gamma of dimension only polynomial to the k over epsilon, such that we can compute a clustering objective over the projected points pi x, which is always a good approximation for the clustering objective over the original data set. So the idea is to show that for any k-center set C, the sum of the difference between two projected distances is always very small. So we make a projection. If we make a projection from x to pi x, the x pi x, and for each center C projected to C0, we can find that this is actually k-median value over the projected point set f gamma x. And then the dimension of these projected points is only the dimension of subspace gamma plus 1, say just poly k over epsilon. And then we can apply importance sampling on these projected points. And so by this way, we have a core set of size only poly k over epsilon. And further, we can use a recent result of terminal embedding to reduce the size to O tilde k over epsilon to the 4th. And this approach can be extended to general Z. It sounds everything is good. What's the problem? So first, constructing this subspace gamma is not very easy. In fact, in the Solar and Wuzhov paper, it costs an exponential k over epsilon 1 time, and this has been removed in a very recent paper. And another problem is that by this way, the core set S is in R e plus 1 instead of a subset of the original data set. And then we may need to design new clustering of algorithms on the core set, and because the computation function of clustering objective may change. To address these two problems, a natural idea is whether we can only use importance sampling to construct core sets and of the same size. The answer is yes. We prove that there exists a two-staged importance sampling framework, achieve the same size core set size, and the running time is only O tilde NDK. So the main idea is that we do not need to construct the subspace gamma explicitly. The existence of this gamma is already enough for our analysis. An important observation is that, in fact, the original dataset X and the projected dataset F gamma X share the same sensitivity function. So if we do importance sampling on the projected dataset, we actually do an importance sampling on the original dataset. So a natural question is that, suppose we have a coset B over the projected point set F gamma X. Maybe the inverse dataset is already a coset. So this is an image to describe this idea. And the main approach is that if we show if S is also a weak coset of X for another important shape-fitting problem called a subspace approximation, then S is a coset for a clustering problem. So it implies an interesting relation between two shape-fitting problems, clustering and subspace approximation. The open question, can we further tighten the size dependence on epsilon? And the full talk can be found on YouTube. And thank you, and question.
Okay, thanks a lot, Ling Chao. Questions for Ling Chao? So I have one question. So does this data structure dynamize? Can you make it dynamic under insertion of new points?
Dynamic, you mean like streaming model or something? Or distributed?
Yeah, but I keep basically inserting or deleting points, and I want to maintain the core set.
Yes. So there is another line of research showing that if you have a offline algorithm, you can always change it to an online algorithm, and so you may need more space, but it can be done, and roughly it's because core set has a composable property or something.
Okay, great. I think Chandra has another question here. He asks to state the main result, I guess, more explicitly.
Oh, okay. Sorry. Okay. So our main result is that before I explain the work of Solar and Wuzhou, so they need to first construct a subspace and project all points to the subspace, and then construct coset on that subspace. And so the problem is that this construction for the subspace gamma is not very easy. So we show that we only need to do importance sampling on the original data set. So just take samples following from some distribution computed by the sensitivity, determined by the sensitivity function. And by this two-stage sampling, we can achieve the core set with the same size as Solar and Wuzhou, and the running time is only 0.2 NDK.
Okay. Great. I think that answers Chandra's question. Another question, where does the exponent 2z plus 2 come from? Can you say something about this?
Okay. So it's because here, actually, the construction of gamma, you need to satisfy this property for any k point set C. The distance between two projection distances is small, and so because this C, this inequality should hold for all center set C. And there are many centers at C in the Euclidean space. So to achieve this gamma, it needs so to construct this gamma is not very easy, and roughly it applies some metric multiplication and something. So detail you need to read the Solar and Woodruff paper, but here I roughly explain the difficulty.
Okay, thanks a lot. Just to make sure, you need to show for your result that the solar Woodruff dimension reduction preserves not only the distances in the reduced in the smaller subspace, but also the sensitivity scores, right?
Sensitivity score is independent. So Feldman and Lemberg has shown how to construct the sensitivity function. And Solar Woodruff show that by this dimension reduction approach, we can reduce the, in fact, it's the something called visit dimension or shortening dimension. That's what we need to bound. So there are these are two issues, independent issues.
Okay, thanks a lot. More questions for Ling Xiao? All right, thanks a lot, Ling Xiao. I think we can stop sharing the screen. Thank you. And we're moving to the last talk by Eric Bolkonski, who's going to talk about lower bounds for parallel submodular minimization. So Eric, the stage is yours.
Thank you. Yeah, so I'm going to present a lower bound for parallel submodular minimization. And this is joint work with Yaron Singer. So I'd like to begin with the current state of submodular minimization. So this is a fundamental discrete optimization problem. It generalizes many important problems such as min-cat, and it has applications in areas such as image segmentation and speech analysis. So it's actually known since the early 80s that the problem of submodular minimization can be solved exactly using the ellipsoid algorithm. However, the ellipsoid algorithm is very slow in practice and requires a very large number of queries to the objective function. So this has motivated a long line of work, a lot of which is very recent, with the goal to accelerate submodular minimization by reducing the query complexity. So in particular, to date, for the general setting, the best known query complexity for submodular minimization is n-cube. So a natural way to accelerate computation is by using parallelization. And since all of the previous work that accelerates minimization is in a purely sequential setting and tries to reduce the number of queries by just reducing the number of queries, one might wonder if we can use parallelization to accelerate submodular minimization. So how do we measure parallelization? So for that, there is the adaptive complexity model, which was recently introduced in the context of submodular maximization. So the standard approach, the standard measure for the complexity of black box optimization is by just counting the total number of function evaluations that are done by an algorithm. And so here, we're going to consider a simple model where the algorithm can perform multiple function evaluations in parallel. So we say that an algorithm is R adaptive if it consists of R sequential rounds, where in each round, the algorithm can perform many function evaluations in parallel. Okay. So this is adaptivity. So there's been a lot of recent progress on the adaptive complexity of submodular maximization over the past 2 years. So recently it was shown that there is actually an algorithm that uses only logarithmically many rounds, and that obtains a constant factor approximation for maximizing a monotone submodular function under quantity constraints. And since all of the previous constant factor approximation algorithm for submodular maximization had at least linear adaptivity, this was an exponential improvement in the adaptivity, so the power runtime, compared to any previous constant factor approximation algorithm. And so this result started a very recent line of work on the adaptive complexity of submodular maximization. And the recent result that's the most relevant to this work is that for the problem of unconstrained submodular maximization, there's actually an algorithm that uses only a constant number of adaptive rounds and that obtains an approximation that's arbitrarily close to the optimal 1/2 approximation. Okay. So unlike submodular maximization, where the adaptive complexity of maximization submodular function is starting to be very well understood, very little is known about the adaptivity of submodular minimization. It's very poorly understood. So the algorithm I mentioned that has the best n-cube per complexity, it consists of at least n square, at least n squared iterations. So it has adaptivity that is at least n squared. And all previous algorithms also have adaptivity that is at least n squared. There's also a recent result that shows that if an algorithm for submodular minimization had subpolynomial adaptivity, then we need to have correct complexity that is at least close to quadratic. So for the general setting where we allow many queries per round, the number of rounds needed, so the power runtime of submodular minimization, all that we know is that it's somewhere between 1 and n squared. So now we're going to present our main result. So our main result is that we initiate the study of the adaptive complexity of submodular minimization by giving the first non-trivial lower bound. So we show that there's no literal log n over log n adaptive algorithm that can solve submodular minimization with constant probability. So this is a lower bound that holds for both deterministic and randomized algorithms. As I mentioned, it's the first lower bound for the power runtime of submodular minimization. In fact, it's actually the first lower bound for the power runtime of unconstrained submodular optimization in general, for either maximization or for minimization. So now I'm going to quickly just mention some main ideas for the analysis. So we want to construct submodular functions that are hard to minimize. So these functions are going to depend on the partition of the elements into R+2 different parts. So this is for lower bound on R adaptive algorithms. So what we want to do is have a function that depends like this on R+2 different parts, such that the set PR+2 is going to be the optimal solution. And we also want to have it such that after I rounds of queries by the algorithm, the sets PI+1 through PR+2 are all indistinguishable to the algorithm. So what that means is that initially, the algorithm cannot distinguish any of the elements. All of the elements look the same. After one round of queries, the algorithm might be able to learn which elements are in the set P1, but all of the remaining elements are still indistinguishable, and so on. And so after all rounds of queries, we have that the sets PR+1 and PR+2 are indistinguishable. And since PR+2 is the optimal solution, the algorithm cannot find the optimal solution. So this property of indistinguishability, we want to show that the elements in PI+1 through PR+2 are indistinguishable is the main lemma that we want to obtain. And so the main idea to be able to construct a function that satisfies this lemma is the following. So let's say that after I-1 rounds of queries, the algorithm cannot distinguish elements in PI through PR+2. Here, what we will do that we're going to use the elements in part PI to mask or hide the difference between elements in PI+1 through PR+2 in the queries as round I. So that after these queries as round I, the elements in PI+1 through PR+2 are indistinguishable to the algorithm. Okay. So to conclude, we initiate the study of the adaptivity or the power runtime of submodular minimization by giving the first lower bound for the power runtime of submodular minimization. Thank you.
Okay, thanks a lot, Eric. Questions to Eric? So Eric, what is the number of rounds of the best upper bound?
Yeah, so the best Crowley complexity is n cube, and this has at least n squared iteration. So the best upper bound would be at least n squared. I don't know. I'm not sure exactly what it is, but it's at least n squared.
Okay. More questions to Eric? All right. If there are no more, there is one question by David. Any chance the ideas of your algorithm of your lower bound can give lower bounds in terms of epsilon on the adaptivity for half minus epsilon submodular maximization?
So the question is whether this lower bound could help to give some lower bounds for the unconstrained submodular maximization.
For half minus epsilon submodular maximization.
Yeah. Yeah. So these lower bounds for submodular minimization, since they have a very different structures than the previous lower bound for submodular maximization. They're really designed for the boundary minimization, so I don't think they would be able to be used for submodular maximization.
All right. Thanks, Eric. All right, everybody. So if there are no more questions, this concludes the session and, in fact, the entire conference. We can feel free to hang out for another like 10, 15 minutes if the speakers have the time. So feel free to hang out a little bit more. And thanks everyone for joining, and to the speakers, the technical support. That's it. So be safe and have a good weekend, everyone. I think we can stop recording.